Okay, so in this video we're going to be seeing, I think, a really remarkable result known as the fundamental theorem of calculus. So as the name implies, it's fundamental. It connects a lot of the ideas that we've discussed so far in the class, specifically the two big ideas of differentiation and integration. So we're not going to prove the fundamental theorem of calculus. That's beyond the scope of what you're expected to know in this class. But I would like to provide some intuition for why it's true. And so the argument I'm going to give is not entirely rigorous, but will end up at a rather surprising result at the end. So it'll sort of seem like I'm starting with something unrelated to what we've been doing at first, but then you'll see at the end that we arrive at something interesting. So I'm going to start off with just some differentiable function capital F. And I'm going to have the derivative of this function be denoted by little f. And so suppose I want to know what's the total change in f between 2 points A and B. Well, this is not too difficult to find. It's f of b minus f of a, right? So the change between these 2 points is just the function value at the second point minus the function value at the first point. So now, in some sense, we've already solved the problem, right? We would just subtract these two function values. But instead of doing it this way, I want to do it a more complicated way, for, at the moment, seemingly no good reason. So what I'm going to do is divide the interval a to b into n pieces. And we're going to do this the same way we've been doing for the definite integral. So we'll have x0, which is the same as a, x1, x2, x3, all the way out to x sub n. And so I can write that f of b minus f of a is equal to f of b plus negative f of xn minus 1 plus f of xn minus 1. And so obviously this is true because this term here is just equal to 0, so I haven't done anything really. Then I'm going to add more terms like that. Again, this is the same as adding 0, so it doesn't really affect anything. I'm going to keep adding terms, f of x1 minus f of x1. I guess I wanted it the other order, but it won't really matter all that much. Then finally, I have minus f of a, which is the same as f of x0. So I have f of xn minus f of x0, and then a bunch of stuff in between that all just cancels out to 0. Now, it may not be obvious why I'm doing this, but I can rearrange these terms. So I'll have f of b minus f of xn minus 1. I'm going to rewrite f of b as f of xn. Then I have a plus f of xn minus 1 minus f of xn minus 2. And I keep grouping the terms like this until eventually I get to the last term is f of x1 minus f of x0, which is the same as f of a. And so I can write this compactly in sigma notation as the sum from k equals 1 up to n of f of xk minus f of xk minus 1. Okay, so I've taken something that was relatively easy, the difference of two function values, and turned it into a big complicated sum. And so you may be thinking this is not much progress, but let's just see what more can be done here. So this difference, actually, it's a difference of two nearby function values. And so we could approximate this difference using a linear approximation. So if we do a linear approximation to f at xk minus 1, then we'll get that f of x minus f of x k minus 1 is approximately equal to f prime, which is little f, of xk minus 1 times x minus xk minus 1. Now, if we evaluate this linear function at xk, we see that f of xk minus f of xk minus 1 is approximately equal to f of xk minus 1 times xk minus xk minus 1. And we notice that this is the difference between two successive x values. That's what we've been calling delta x. So we have that f of b minus f of a is approximately equal to, well, okay, it's exactly equal to the sum from k equals 1 to n, f of xk minus f of xk minus 1. That's what we had before. And then that is approximately equal to the sum from k equals 1 to n of little f of xk minus 1 times delta x. Now, you might not like this k minus 1 inside the sum, but you can rewrite this sum by changing the index. Since we're subtracting 1 from the value, this is the same as summing starting from 0 up to n minus 1 of just f of xk. So this is known as re-indexing. So we're changing the index of the sum, but we're also changing this k minus 1 to a k, so that the terms are still the same, but it looks more similar to what we've seen before. In particular, this looks a lot like a left-hand sum for the derivative function, little f. So that means that this, if n is a big number, will be approximately equal to the integral from a to b, little f of x dx. So let's stop and now think about this in reverse. If we're given a function f of x, we want to find the integral from a to b of this function. Then this is saying that it should be close to the value of f of b minus f of a, where f is the antiderivative of little f. Or capital F, I should be specifying when I say f. So capital F is the antiderivative of little f, so the integral from a to b of little f is going to be close to the capital F of b minus capital F of a. And so I've put an approximately equal sign here because I did some questionable steps. Specifically, I replaced this difference by a linear approximation, and I just replaced this Riemann sum with an integral. But if you do a little bit of more careful analysis, then you can actually show the fundamental theorem of calculus, which is abbreviated FTC. And this says that if f is continuous and the derivative of capital F is equal to little f, then this is actually an exact equality. Integral from a to b f of x dx is exactly equal to f of b minus f of a, capital F of b minus capital F of a. So this is really useful because it means that if we can find the antiderivative, capital F, then we can evaluate the definite integral just by looking at a difference of values of the antiderivative. So let's see some examples of how we can use this. So let's suppose we look at something that we actually looked at in the last lecture, integral from 0 to 1 x squared dx. And I claimed that the value of this integral was 1/3. And we saw from Riemann sums that that was reasonable. It was very close to what we're getting with Riemann sums with like 10,000 rectangles. But how can we prove that that's the true value? Well, we want to use the fundamental theorem of calculus. So we first have to find an antiderivative of little f, which is x squared. And we've been doing lots of stuff with antiderivatives, so hopefully you're familiar with the antiderivative of this function. It's 1/3 x cubed. I'm going to put a plus a constant for now, but we'll see that this constant actually does not matter. So now by the fundamental theorem, this is equal to f of b minus f of a, which in this case is f of 1 minus f of 0. And if we plug in our function, that means it's 1/3 times 1 cubed plus c minus 1/3 times 0 cubed plus c. And so this term here gives us the 1/3. This is 0, and then notice that no matter what the value of c is, you'll get a plus c in the f of b term, then a plus c with a minus sign in the f of a term, so the c's will cancel out and didn't end up making any difference at all. So we just end up with 1/3. By the way, it's common at this step to write something like this to mean exactly as a shorthand of what I've written here. So if you see this notation, it means take 1/3 x cubed, plug in 1, and then subtract what you get when you plug in 0. You will also often see me write this. So this is just a habit of mine. I prefer to write something like this because then I can clearly see that this is this entire thing that's getting evaluated, whereas with this, if there was some stuff in your equation on the left, then maybe it would be less clear. But this notation that I use is not so standard, so I recommend that you stick to this, and I will try to do that also. But if you see me do this, then that's just a bad habit of mine. Okay, so let's look at another example. So let's suppose that we want to find the integral from 1 to 2 of, let's say, 1 over x squared dx. So in this case, our antiderivative of this function is going to be equal to negative x to the negative 1. And as we discussed in the previous one, it doesn't matter if we ignore the plus c. So this means that by the fundamental theorem, the integral from 1 to 2, 1 over x squared dx, is going to be equal to negative x to the negative 1 from 1 to 2. And this thing will be equal to negative 1 over 2. That's what happens if I plug in 2 to this function. Then minus negative 1 over 1. That's what happens when I plug in 1 to this function. And so this means it's negative 1/2 plus 1. That gives me a total of 1/2. So as you can see, the definite integral, I think, a lot of what we've been doing so far seemed rather complicated with like these big Riemann sums and areas under these strange looking curves. But really, once you have the fundamental theorem, it's fairly straightforward to calculate these things if we know the antiderivative of the function inside the integral. And so this is not necessarily because the definite integral is a simple object, it's just because the fundamental theorem is a really powerful tool. It lets us calculate something that's fairly complicated in a comparatively straightforward way. So I think this is one of the remarkable facts in calculus. Okay, so let's do just a few more examples so that you can get used to these sorts of problems. So suppose you want to find the integral from 0 up to pi of sine 3x dx. Well, the antiderivative of this function will be 1/3 cosine of 3x. And then because the derivative of cosine is minus sine, we need a minus sign out front here. So therefore, the integral of 0 to pi sine of 3x dx is just going to be equal to negative 1/3 cosine 3x from 0 to pi. If we plug in pi, we'll get cosine of 3 pi, which is negative 1, so that becomes 1/3, minus cosine of 0 is 1, so that means it's negative 1/3. So overall, we'll get 2/3. Okay, and let's do one more example in this video. So let's find the integral from 0 to 1. Yeah, that's fine. Of 1 over 1 plus x squared dx. Okay, so the antiderivative of 1 over 1 plus x squared dx is arctan. We're evaluating from 0 to 1. Arctan of 1 means that tangent is equal to 1. That occurs when sine and cosine have the same value, which you may recall happens at pi over 4. Then if we plug in 0, arctan of 0 is equal to 0. So the value of this integral is pi over 4. And so I'd like to point out, in the earlier examples, I sort of wrote out more detail, right? So I wrote out what the antiderivative was, then I wrote out f of this minus f of that, and then wrote out a lot of steps. That was because it was the first example we were looking at. Then in these examples, I wrote the antiderivative, then used this shorthand notation and wrote a bit fewer steps. And now in this last example, I barely wrote any steps. So you can sort of write out as much detail as you're comfortable with as far as these two extremes. But I think it's fine if you do something more brief like this. I think the key steps that are important for you to show when you're solving one of these problems, the integral, the antiderivative and where you're evaluating it, and then the final answer that you get. So you definitely have to have these three components, but how much else you write is up to you and how much you think it's helpful.